Hello everyone. This week's lab is going to be conservation of momentum. Momentum is especially useful when dealing with collisions and trying to get information from collisions. So as you can see here, we have different types of collisions, and we'll be talking about those towards the end of this presentation here. But let's go ahead and get going. Thank you. Now, if you were to make billiards balls, would you make them hard or soft, like a tennis ball? Think about why billiards balls or bowling balls, why are they made of a hard material? Why are tennis balls and soccer balls not that hard? Why are they soft and flexible? This is what we'll be talking about. All right, before we get going, we need to start talking about some concepts and quantities. This is what most of this lecture is going to be about, is covering some of the background information needed to start dealing with collisions. Newton's third law, also known as equal and opposite, is when one body exerts a force on a second body and the second body at the same time exerts a force equal in magnitude and opposite in direction on the first body. Hence the equal and opposite. When you walk, you apply a force backward, but you move forward. That makes sense. Rowing is another example of Newton's third law in everyday life. Well, not around here anyway, but yes, it is an example of Newton's third law. They row one direction, and then of course the motion is in the opposite direction. Momentum. We simply define momentum as mass times velocity, but it has a whole lot more to say than just that. So momentum, P, equals mv. Now, when I was putting this together, I was wondering, why is it called, why do we use P for the letter? But it turns out that before it was called momentum, they used the term impetus, and then which came from the Latin root word petere, P-E-T-E-R-E. I don't know how to pronounce that properly in Latin. But that is where P comes from. Anyhow, so P equals mv. Notice that it is a vector quantity. So vector quantities means, yes, we have to pay attention to direction and magnitude. So P equals m times v. And then the units of those, you have mass is in kilograms, velocity is in meters per second. So the actual units that you'll use is kilogram meters per second. For example, we're going to take a look at a truck. It has a mass of 1,200 kilograms, and it's moving at a velocity of 3 meters per second. Then we have a nice little car that is 400 kilograms and moving at the same speed. Now, if P equals mv, got 1,200 kilograms times a positive 3 meters per second in the I direction, notice because it's moving to the right, is a positive 3,600 kilogram meters per second. So that is the momentum. For the car, you have 400 kilograms times a negative 3 meters per second in the I direction, so that's moving to the left, and you have a negative 1,200 kilogram meters per second. Pay attention to that sign. How you set up your coordinates is going to be very important. Remember, whenever you set up your coordinates, you have to use the same coordinate system through the whole problem. Now imagine you want to stop either the car or the truck in 10 seconds. Which do you think would be harder to stop? Come on, take a guess. Yeah, I think you probably got it right. Okay, so F net, so the net force equals mass times acceleration. We've covered that numerous times, and I'm sure you've heard it in your lecture multiple times too. However, acceleration can also be defined as delta V over delta T. And then we take that little m and move it up next to the v, and we have delta mv over delta t, which is mv is also known as momentum, which is p. So delta p over delta t is also equal to the force. There, that was a derivation. That was lots of fun. This means that when you apply a net force of F net on an object over a time period of delta t, the momentum of the object changes by delta p. Or just the opposite, if you want to change the momentum of an object by delta p, you need to apply a net force for an amount of time. Now let's find out how much force we need to apply to stop the truck and the car. Let's see which one's harder to stop. Okay, if we want to find the force that is necessary to stop the truck in 10 seconds, we need to look at first our delta p, our change in momentum. So our initial velocity is 3 meters per second. We know that the mass is 1,200 kilograms. So we know our initial momentum, which is 3,600 kilograms meters per second, in the I direction, which is in the positive x direction. Now 10 seconds is our delta t. Our final velocity is 0, which means our final velocity times 1,200 is 0 momentum. So if our change in momentum is your final minus your initial, we've said that before. So final is 0 minus your initial, and it's all in the I hat direction. So the change in momentum is negative 3,600 kilograms meters per second in the I direction. So the force is your delta P over your delta T. Your delta P is negative 3,600 over your delta T is 10 seconds. So that ends up with negative 360 newtons in the I direction. So that's basically, it's to the left, which makes sense because it's slowing down. Next, we have the car. Its initial velocity is 3 meters per second and has a mass of 400 kilograms. So the initial momentum is negative 1,200 kilograms meters per second in the I direction. 10 seconds is the same time frame. The final velocity is also 0, therefore the final momentum is 0. Doing the exact same thing, we have your final minus your initial momentum, which is 0 minus a negative 1,200, which ends up being a positive 1,200 kilograms meters per second in the I direction. The force net is delta P over delta T, which is 1,200 over 10, which ends up being 120 newtons in the I direction, which is, of course, going to the right, which makes sense because the car is going to the left and is slowing down. All right, now we're going to talk about collision. So let's see what happens. Imagine two objects collide. We would like to see what is happening at the very exact instant that they collide while the objects are in contact. So this is happening just as they touch. So we have the two blocks that are on a frictionless surface, of course. They're going to come together. And at the moment that they touch, we have two free body diagrams. Notice that we have them labeled properly. You have, for the blue, we have the gravitational force on block B by the Earth, the normal force on B by the surface, and then we have the normal force on B by block A. And then for the yellow one, we have the same thing, but we have the normal force on A by block B. So here is where the transfer of momentum happens. Now first, let's look at the forces. The force net is going to be the addition of all the forces that we have in each free body diagram. So notice that the normal force and the weight are the same in this instance because it's on a flat level surface. And so what do we have left over? We have the normal force on B by A. The same thing, we have the net force on block B, or I'm sorry, on block A is the only thing that's left over after your normal force. The normal force and the gravitational force cancel each other out. We have the normal force on block A by block B. So the net force is the normal force for each, which means that Newton's third law, that the normal force on block A by block B is equal to the negative of the normal force of A on A by B, which is also means it's your change in momentum of A is the negative change in momentum of B. Now, conservation of momentum. If the net force equals your change in momentum over your change in time, and the net force of the system, where we're talking about our system here, we're talking about two separate things that are in collision, equals 0, then the change in momentum must also equal 0. That means that the initial momentum must equal the final momentum. When the net force is 0, which is usually called an external force, on a system is 0, then momentum is conserved. Okay, here we have three different setups here. A ball is shot towards a target at rest. So the target is just a block, and the block is still at first, and then when the velocity or the ball comes in with a certain velocity, it has a certain mass. Three things can happen. The ball can stop after the collision and the target can move. We'll call that the stopper. The ball can stick to the target and they can move together. We'll call that the sticker. And then the ball hits the target and bounces back, and of course the target moves forward, so we'll call that the bouncer. In which situation does the target move faster after the collision? For the stopper, let's assume the ball has an initial momentum whose length is shown below. There we go. So there's our initial momentum. Now remember, momentum is a vector quantity, so arrows are going to be very important. Remember, the length of the arrow is proportional to the amount of momentum that the object has. So your final momentum is 0. So your change in momentum is going to be your final minus your initial, which is 0 minus your initial momentum, which equals negative pi. And then for the target, you have your PT equals your PF minus your PI. PF minus 0 ends up being just the final momentum. So here we have your delta PB is going to point the other direction because it's your final minus your initial, so it's the negative of your initial. And since PB equals negative delta PT, we have that it's going to point in the opposite direction. Now make sure you note the length. As before, we have the same initial momentum. The final momentum, it has a little bit of momentum going forward because remember it's stuck and they both moved forward at the same velocity. And then, so here we have the same procedure where we're looking at the final momentums. And so your final minus your initial equals your change in. There you go. We've done this before. And so once again, we go through that. So your change in momentum of the target is, there you go. And it is slightly less. Now the bouncer, here we have an initial momentum. We have a final momentum. Our final minus initial ends up being huge. So same thing, it's going to be also quite huge. So the target is faster in the bouncer situation. That is why billiards and bowling balls are hard. It's also the same reason for tennis balls, soccer balls, because they create an elastic collision where all the energy is conserved. Speaking of energy, there are two types of collisions, elastic and inelastic. Elastic is, think about elastic is when no deformation happens. That the the objects that collide are in the same, they're in the same shape after the collision as they were before the collision. An inelastic collision is going to be where there is deformation. So think cars crunch. That's an inelastic collision. So the main difference between an elastic and inelastic collision is when kinetic energy is conserved. While an inelastic collision, it is not, because some of that energy goes into the deformation process. So here we go. Here's the picture that we started off with. Here's our collisions. We have the football players. That's an inelastic collision. The billiards ball, that's going to be an elastic collision. Newton's cradle, that's an elastic collision. The bowling ball and pins, that is an elastic collision. But that looks like all. So we'll look forward to seeing you guys in lab. Talk to you later. Bye-bye.